Thank you, Ms. Solano. Well, it's sometimes the story of my life. I somehow fall behind even before starting. I know I'm 15 minutes late, so I'll try my best to keep my presentation crisp and short because I don't want to kill much of your break time. So I'm here today to present our study on material flow analysis of global battery nickel supply chain that we call Seeing the Midstream, Trade-Based Reconstruction of Battery-Grade Nickel Flows and the Mislocation of Critical Mineral Policy. So as Dr. Alana said, I graduated from the University of Alberta, and ever since I've been working here at S&T. The introduction made me sound important, but I sometimes feel that I'm kind of professional in the middle of no man's land right now. Neither a student nor a faculty here. I work as a postdoc, but I have been incredibly lucky and blessed to work with an amazing group, the Mine Sustainability Modeling Group with Dr. Kwame. How do you work with this? Oh, okay. Okay, yeah. So in my presentation, I'm going to go over the problem we are trying to address, the incredibly hard to see bottleneck in battery nickel supply chain, the approach and scope of the research, our key findings, and some policy implications and recommendations. And as I said, I'll try my best not to bore you. Nickel supply risk is often framed as a mining problem. We tend to ask the question, do we have enough mines to extract nickel? But for batteries, that's not really the complete picture. Nickel has to go through a specific conversion step to be useful for battery-grade chemicals. Many countries can mine nickel, as you can see in this slide: Philippines, Indonesia, Australia, Canada, New Caledonia, and many others. But the conversion step, or the options to convert those nickels into battery-grade chemical, is limited. So that's where the global choke point is usually at, and therefore the bottleneck is not who can mine nickel or how much ore we have, but who can convert those nickel into battery-grade chemicals. The problem is that the midstream is incredibly hard to see. So the trade data that we have has trade codes that are sometimes too broad and generic, ending up mixing battery-grade materials with the non-battery-grade materials. The trade values are almost always in dollar value, obscuring the actual metal tonnage that flows through the supply chain. And we very often see exporters and importers recording or reporting very different numbers when it comes to trade values, causing mirror data gaps. Now, all these things actually contribute to making the battery-relevant intermediate flows hidden, almost invisible. Our research has shown that the finished product code for nickel oxides and hydroxides makes only 10% of the actual nickel that flows through the supply chain. So we therefore have generated a trade-based reconstruction of battery nickel supply chain. We use the bilateral trade data that is publicly available in UNComTrade or WTS database. We use the data between 2022 to 2024. We started by going downstream, looking at the biggest exporters of nickel oxides and hydroxides to identify where the refining happens, the refining hubs. Then we went all the way back upstream to see which countries provide those hubs with what material. We converted the dollar values into content nickel. As a final step, we screened out the non-battery routes from the battery routes so that we can reconstruct the battery-relevant flow that consumes the supply chain. Therefore, the output of this study is a facility-informed picture of who controls the conversion of the intermediates. I kept this slide because I did not want to oversell our research. While I would love my research to be as global and universal as Dr. Einstein's theory of relativity, but we have our limitations and boundaries. So we have considered the battery-relevant nickel, such as the ore, MHP matte, nickel sulfate, into our study, but non-battery routes like the nickel pig iron, ferronickel, etc., fall beyond the scope of what we have done. We identified and worked with the refining hubs. So we do not claim this research to be a global mass balance closure. We used contained nickel as the basis of our calculation and screen suppliers like Russia, Cuba, that are subject to US sanctions. So moving on to the findings, the first one is a pretty obvious one. Over 77% of the reconstructed battery-relevant inflows go to or through China, which amounts, according to our study, almost about 368 kilotons of nickel per year. Japan and Australia receive far smaller but more specialized intermediate streams. The Sankey diagram on the right-hand side shows what amount of different materials flow from the supplier countries to these refining hubs. The second finding is about addressing the elephant in the room, right? So not that only we have one hub, we have one supplier that controls almost 75% of China's battery-relevant nickel. So the raw material almost entirely comes from Indonesia. That makes the import in the Chinese supply chain extremely concentrated, and the HHI value is almost 5,700. Now this shows that the market is extremely concentrated, and this HHI value is almost twice the threshold value we use in criticality work to measure concentration. Japan has a slightly less HHI index, 4,000, but they are also concentrated. They depend on Indonesia and Philippines for their nickel supply. This concentration in import actually propagates to export too. Exports often funnel into single corridors. For example, China exports almost 93% of their battery-relevant nickel to South Korea. Australia exports almost 90% of their nickel to China. Japan is an exception, but their market or their share is not as big as China or Australia's, at least for the decision time frame from 2022 to 2024. The fourth finding is about visibility. So the finished product trade codes actually captures a very small percentage of what actually flows through the Chinese precursor system. So in simpler terms, we can see that the visible trade is just the tip of the iceberg, right? So, and again, we have mirror data discrepancy, which can be over 270 to 500 times. China reports almost $1 billion of nickel oxide hydroxide export to Korea, South Korea, and South Korea reports only $2 to $4 million. Now, this huge mirror discrepancy actually makes one of the largest corridor inside this supply chain network nearly invisible if you are looking at the import data only. China reports about $1.1 billion of nickel oxide hydroxide export within the period 2022 to 2024, but our study shows about $7.9 billion of contained nickel flowing through their supply chain. This actually makes sense because much of the nickel that flows through Chinese supply chain is used in their domestic lithium-ion battery production, which is later exported as lithium-ion battery. As you can see, the battery export from China is almost $59 billion. So we offer 3 levers of resilience, or 3 recommendations. Number 1 is that we somehow need to diversify the conversion capacity. Maybe building some strategically located refining capacities across the globe can help us reduce the over-dependence on only one hub. Number 2 is to think about the resource-rich countries like Australia. They need to add more value to their upstream by converting ore to finished products instead of just choosing to export raw material or partially processed concentrates to China and other countries. And number 3 is that we perhaps need finer custom codes so that the intermediates and the finished products like MHP, matte, sulfate can be more easily captured. And of course, we need some reconciliation in the importer-exporter reports of the trade value so that we can reduce the mirror data discrepancy that we have. So the message, in short, is that the concept of total nickel can be misleading, right? The nickel used for batteries is not the same as the nickel used for stainless steel, per se. So the battery-relevant nickel needs to go through specific steps, like from MHP or nickel matte to sulfate to nickel hydroxide all the way to cathodes. Right? If the policy looks only at the total nickel, it might actually end up missing the actual bottleneck that happens inside this conversion phase of battery-relevant nickel supply chain. So the takeaway from all of this is the identification of the fact that battery nickel risk does not lie in who mines how much or who ships, but it lies on who controls the conversion. So we have produced a low-cost transferable method for locating hidden processing choke points or bottlenecks that can also be extended to other minerals like lithium, cobalt, graphite. We identified one refining hub that controls about 77% of the battery-relevant nickel supply chain. One supplier that provides almost 3/4 of Chinese battery-relevant supply raw materials and invisible corridors of trade due to huge mirror data discrepancy. Thank you very much, everyone. That was all from me. The student in me is still alive and does not really want questions, but I'll be very much very happy to answer any questions you guys have, if we have any. Well, yeah. Okay, thank you so much.
Not
oh,
quite
we have a question?
free
Okay,
yeah.
that's good.
You said that applies to nickel, but then you also mentioned, lithium and other things. Is that, it seemed like it was really obvious in nickel what was going on.
Right.
Are the other metals like that as well?
Actually, what I talked about there is the methodology, right? So this is a trade-based reconstruction of the supply chain. So the methodology we proposed can be extended to other minerals. So we are not quite, because this was on nickel, so we don't know what is really happening with lithium or cobalt, but this methodology can be transferred to cobalt, and we can look at the bottlenecks for, let's say, cobalt or lithium.
Please join me in thanking Dr. Al Habib.